We'll continue this time and trying to explore a little bit more. And now, so before I was talking more about the idea of quantum simulation, ultra-cold atoms. Now, in this part, I want to focus a little bit on entanglement generation and how we are going to use atomic systems for understanding the dynamics of entanglement, basically. Oh, it's not working? Okay. Oh, okay, I see. Okay, perfect. All right, so as I said, our goals is trying to generate with ultra-cold matter quantum simulators of condensed matter systems, and in particular the phenomenon of quantum magnetism. We want to generate, we utilize these systems to engineer quantum computers. We want to use these systems for understanding fundamental physics, and in particular, we want to unravel the mystery of quantum gravity, black holes, and quantum matter. And we want to use this system for create very ultra-precise sensors. And one of the systems that actually is able to touch into all these different directions are systems of trapped ions. So this is what we are going to talk today. Unfortunately, it seems that the tours to Nice are going to be canceled because of the government shutdown. But this research, what I'm going to talk about, is going to be very highly connected with the research that is happening there. It's 10 minutes by car from here, from Boulder. All right. So the trap ion systems that I want to focus in this talk are the ones that forms two-dimensional crystals. And these type of systems, how they create this type of system is using what is called a penning trap. So the basic idea is that they have the ions, and they confine in a set of stacked electrodes that create a very strong confinement along the z direction. So this is the way that they can confine the atoms in almost a single plane. And in addition, what happens is that they have a rotating wall. And this rotating wall, in the presence of a very strong magnetic field, so they have a superconducting magnet of the order of 4 Tesla, generates a Lorentz force. And this Lorentz force is what confines the ions along the radial direction. So we have both axial confinement from the electrons and radial confinement from this rotating wall. And the ions, because of the Coulomb repulsions, self-assemble themselves in the form of two-dimensional triangular lattices. So these are real experimental pictures taken in this system. You can see that each of these bright points are ions. And actually, in these penning traps, they're able to trap arrays that goes between 20 ions to almost 300. The complexity of this system is that it's rotating, and that's why single ion addressability is a little bit more complicated than in the standard setups that it have 1D change, that is the pole traps. But the advantage of these systems is that they can trap very large arrays, and therefore with this very large arrays, we can try to emulate more complex behavior. So these are our systems. And well, what we want to do is we use encode a qubit in each of the ions. And in order to do that, what we choose are hyperfine states, the lowest two hyperfine states of beryllium ions. So we are using beryllium ions. They are charged, and we are using the two lowest hyperfine states as our spin 1/2 system. So the splitting between these two states is actually quite large compared to other atomic systems. It's the order of hundreds of gigahertz. And the reason is because we have a very large magnetic field. It's from these superconducting magnets. But at this energy splitting, we can use microwaves to actually implement our, single qubit gates. And actually, they can reach a very good fidelity in controlling each of the qubits, individual qubits, and the fidelity can be of the order of 99.9 fidelity. Okay, so, but we want not only to control individual particles, what we want is to correlate them, to entangle them, and the way that we need to entangle them is actually via interactions. The point is that if you look at the distance that these ions are separated, it's so large that we cannot count like natural exchange interactions, such like the ones that I was describing before, the super exchange interactions to introduce spin-spin interactions. They are too weak in these systems in order to generate the interactions at the level that we want to. So the only way that we can make these systems interact is to engineer artificially these type of interactions. And as usual, the way that we manipulate and engineer this type of interactions is through lasers. There are very different ways to generate gates or 2-qubit gates in the ions, but the type of 2-qubit gates that, that are engineered in this penning trap are the ones that use Raman field. So they have two lasers at two different frequencies, omega and omega plus nu. These different frequencies engineer like a moving lattice. And this moving lattice introduces kind of forces in these two atoms, in these two qubits, spin 1/2. But because they are separated by an energy difference, so the force that the spin up and the spin down feel is different because of this detuning. So after all, without entering into much detail, what happens is that by illuminating the atoms with these forces, what we create is what is called a spin-dependent force. That means if I have an atom in a spin up, it has a force that is in the opposite direction of a spin down. So this the z direction and sigma c. So it's plus and minus for the different states. And the force is introduced by this detuning nu. So you can see that there is this nu t, and this nu t, this detuning is what is going to allow us to control what type of interactions and the range of interactions we are going to engineer. So let me explain how is that done. The point is that we are going to illuminate our crystals and they are going to experience this type of force. So the force depends on the position of the ion J at site J. And the point is that when we illuminate the ions and they start to move, if one ion moves, the other is also going to move because they are correlated by the Coulomb force. So they form a crystal, and therefore the only way that they can move is through the excitation of the crystals, and this excitation of the crystals are phonons. So what happens is that if we want to actually compute how these forces that we are engineering by the lasers are going to act on the atoms, what we need to do is that we need to expand the position of this ion J in terms of the normal modes of the crystal. So there are phonon modes, there is a crystal, and the ions are going to move in the crystal in a correlated way. So actually you can think of the modes, phonon modes of the crystal like a drumhead modes. So there is a picture, a qualitatively cartoon of how the ions move. So these are kind of the drumhead modes. So you can see that there are different type of excitations. Oh, sorry. Oh, let's see if it works. Okay. So you can see that the highest energy excitation is the one when all the ions are moving together, all up, down. Why is the highest? Because there is no screening of the Coulomb force. They feel exactly the same Coulomb force. They're all moving up and down, and is the center of mass. And then there are other type of excitations of the crystal that are, for example, antisymmetric. Well, you can see different type of I'm very confused with this remote. So there are different type of excitations that you have here. And the point is that depending on the detuning that we choose, we can address one of them or many of them. And depending on how we excite our crystal, then we are going to feel, or we are able to engineer different type of spin interactions. So let me explain a little bit how this works. So let me see. So something that is here important is that the C component is expanded in terms of the normal modes of this of the crystal, and these normal modes are going to be from 1 to n. There are different type of excitation depending on the number of ions. So one of the tricks that one uses, so at the end we are exciting the phonons, but we don't want phonon excitations. The phonons are going to enter later in my talk when we want to excite phonons. But ideally, you don't want to have motional degrees of freedom. The only degrees of freedom what we want to use is the spin degree of freedom. And in order to only use the spin degrees of freedom, is that what we want to do is that we want that the phonons are not excited, are only virtually excited. So only they are, the excitation is only through a virtual process that is similar to the way that we generate super exchange interactions when if you have two particles in the same side, it costs too much energy that is just virtual. So similar things we are going to do with the ions, and in order to do only virtual excitations of the phonons, what we are going to do is that we are going to have our detuning here very far detune from the node of the frequency of the normal modes. In that case, creating a phonon costs so much energy, and therefore the effect of the phonons is just to mediate virtually spin-spin interactions between the ions. So the consequence is that when we do that, the effective Hamiltonian, after eliminating the phonons, have the form of SZSC. So it's kind of second-order perturbation theory. And the coefficients here, so this is the C acting on ion I, SZ acting on ion J, and there is a coupling constant J. And this coupling constant J is going to determine the strength is how my detuning, the detuning of the beating node that we are generating with the laser with respect to the normal modes of the different of the crystal, of the different drumhead modes. And these B are the amplitudes that characterize the phonons in the crystals. So this is the form of the coupling constants. And you see that even though it looks quite complicated, and when you look at this expression, it's quite messy, actually, if you plot how these coupling constants changes as a function of the distance, what you find is actually they satisfy a power law. So what you see is that depending on how far detuned you are from the center of mass mode, that is the high energy mode, then you can control these coupling constants to have very different range. For example, if you are very close to the center of mass, such that only the center of mass is excited, then all the ions are moving completely together. So the interactions are all ranged because if every ion in the crystal is doing exactly the same that the other ion. They are feeling exactly the same coupling. So the interactions are completely all-to-all when we are only very, very close to the center of mass and any other phonon modes are not excited. But as we go here, as we go farther away, and we go farther away in the tuning, then we are off resonance of most of these modes. And the farther that we go, we are equally populating all of these different drumhead modes of the crystal. So that translates in some power law interactions where the power law of this depends on the distance with a power that you can see increases from 0 all to almost dipole-dipole interactions. So the maximum value that you can reach is 3. So we want to all 1 to the r to the 0 to 1 to the r cube. And this is the range of tunability that we have of the interactions in these ion crystals. There is a caveat that the farther that we are detuned, if this denominator grows and becomes very large, then the strength of the interactions become very weak. And that's why in emulating longer range interactions is harder because we have to compete with other decoherent sources that we can have in your systems. So you will find out that most of the talk and most of the experiments nowadays in these spinning trap crystals are actually focusing in this regime where the interactions are stronger and we can beat other type of decoherent sources. But still, if we are going to probe the system for very short times, we can access these power laws and we can characterize that actually this is happening. So the question is, how did the experiments to figure out that this is a power law, and how did the experiment measure or verify that the Hamiltonian that we have in the systems is in this form of these Ising interactions. So last part of my talk, I mentioned clock spectroscopy, I mentioned Ramsey spectroscopy. Actually, this is a very powerful tool in atomic systems, and actually most of the probing is done using Ramsey spectroscopy. But in condensed matter, sometimes you hear, instead of Ramsey spectroscopy, you hear about a quantum quench. So they are exactly the same, and let me explain a little bit why. So yes, so we use Ramsey spectroscopy, and what we do, again to repeat it now in the context of these ions, but exactly the same for the clock, we know very well how to polarize all the spins down. It's by optical pumping, so we know how to have all my spins pointing down, and as I mentioned, we know how to apply microwave pulses such that rotate each of the ions, and because they are microwave, they rotate all the ions at the same time, uniformly, so we go from all spins down after a pi pulse, for example, to all spin pointing along x direction, for example. So we do some rotations, and we are going to vary this rotation angle. If the angle is very small, I'm just going to tip a little bit from the equator. If the angle is pi half, I'm going to be in the equator. If the angle is pi, I'm going to go all the ions in the excited states. So this is going to be our control parameter. So I'm going to do this first rotation. Do this first rotation, and then after this rotation, I'm going to let the system. After this rotation, I'm going to let the system evolve until some Hamiltonian. In this case, it's going to be the Ising Hamiltonian. So in this experiment, sometimes, or usually, they have some sources of noise that can be controlled by what is called an echo pulse in the middle. So don't worry at the moment about that. So it's just to remove some type of inhomogeneities, magnetic fields, or after the pi half, we turn on the lasers that implement the spin-dependent force. So we do the rotation. This is done very quickly, so that's why I'm trying to indicate that 30 microseconds is very quick, and then we let the system evolve for some time with the lasers on, and with the lasers on, we are applying this spin-dependent force that generates the Ising Hamiltonian. And what happens in the very simple picture, and this is what I'm going to explain, in the presence of these Ising-Ising interactions, what happens is that my spin is going to rotate and accumulate some phase. And this phase is going to be determined on the JIJs that are characterized by Ising Hamiltonian. So I'm going to let the system rotate for some time, accumulate some phase that is going to give me information about the JIJs, and then I'm going to measure what is the phase that is accumulated, and this is by applying another pulse here that rotate my spins, and then the phase accumulated I'm able to be read by the number of atoms in the excited states. Thus the sequence is very similar to what I explained for the clocks before. So basically, the idea is that we are going to use this Ramsey spectroscopy to verify the spin model that's the case. Second, well, if the system is evolving during the Ising Hamiltonian, well, it's going to generate some entanglement. So I'm going to try to verify that during this time I'm generating entanglement and correlations. And then if I have system of 20 ions, then in principle it's going to be easy to solve. But if I have a system of 500 ions, my computer is not going to be able to solve this classically, and hopefully I'm going to enter the regime that is intractable to classical computers. That's the goal. All right, so let me try to explain the basic physics that one can expect to see from the Ising Hamiltonian. The basic physics is trying to ignore any type of correlations and try to treating my spins as classical systems. So if I have a Hamiltonian in the form that is sigma c, and imagine that I ignore correlations, I mean, imagine that the density matrix of the system is the product of independent density matrix. The dynamics is that each spin I is going to, each spin J is going to have an effective magnetic field, sir, and this effective magnetic field is going to come from the sum of the Jij's sigma Cj. So you are going to have, so this is my spin, and I'm going to determine the Jij sigma ij. So this is the, so my Bi is going to be sum over, my Bj is going to be sum over I sigma Ci G ij. Yes, I'm going to sum over the spins over the other spins, but the idea is that the Hamiltonian sigma C commutes with sigma C. So the sigma C is not going to be evolved at all during the dynamics, and therefore is going to be determined by the sigma C at time equal to 0, and the sigma C at time equal to 0 is just going to be determined by the time that I apply my first pulse. So the sigma C at the beginning is proportional to cos theta. Theta is that, remember that I have all my spins down, I apply my laser for some time, and I rotated my spin to some direction. So this is the initial direction before I apply the Ising model. That's what is going to determine my sigma C. So that means the magnetic field that I'm going to experience is going to be proportional to this term. And then a spin in a magnetic field is going to precess an paraphase that is proportional to this effective field. This is assuming there are not built up of correlations. So this is assuming that the density matrix is a product, and we expect that this is going to be a good approximation at short times. So in that case, what the experiment is going to see, if they are going to measure the population of the atoms in the excited state, as they change this angle theta, they can control by the first pulse of the laser, we are going to see this cosinusoidal behavior in the dynamics for some time, at a fixed time. So this is exactly what they see. So this is the angle theta. They can change it from 0 to 4 pi, and it depends on the time that you apply the first pulse of the laser. And what you are going to see is that you're going to see some amplitude that depends on the sum of the Jij's and some cos theta that oscillates. And exactly this is the behavior. And then the amplitude is going to be dependent on the time. So the longer the time, during the time evolution, the higher the amplitude of this oscillation. And this is exactly what they see. So because of this oscillation from this, they can extract the magnitude of the Jij's, and because they do a collective measurements, and they can extract this behavior that is consistent with the power law that they were expected. So this is the dots are experiment, the solid line is the theory with this coupling constant scaling like a power law, and you see perfect agreement. So that was very exciting. They were able to see first benchmarking that indeed they were trying to emulate this Ising model. But the behavior that they are exploring so far at these very short times is quite trivial. It's just a simple rotation. And they started to see a deviation when they were looking at these points that were when theta was pi half. When theta was pi half, you see that you expect cos theta is 0. So when theta is equal to pi half, the mean field predictions said you will not see any dynamics. And actually, that's not what we saw in the experiment. So let's try to understand a little bit how this deviation of the mean field theory is telling us that the system is becoming entangled during the dynamics. So, of course, the behavior can be extremely complicated, and in order to see beyond mean field behavior, you have to look at longer times. And so the way that they can go to longer times is when the interactions are stronger and they can beat any other source of the coherences. So from now on, what we are going to focus is the case where we are only going to populate the center of mass mode. So we are going to tune our laser very close to the center of mass and very far from these other modes, so they are not populated. The behavior is mainly going to be a very simple Hamiltonian where all the ions are moving in sync together. So this implements a very simple Hamiltonian that is the collective Ising model. And this is the form of a Z squared, where SC is the sum over the spins of each individual ion. So it's going to be a collective operator. And even though this Hamiltonian, you can imagine, is really trivial, all the ions are doing the same, and it's as simple as C squared Hamiltonian. We know very well the eigenvalues. Still, this Hamiltonian is the Hamiltonian that people are using to generate very highly entangled states that are useful for metrology. So the idea, again, is that we are going to prepare our system with all the spins along X. We are going to evolve the systems on this collective Ising model. This collective Ising model in the literature is known as one-axis twisting Hamiltonian. And what we are going to try to understand is what is entanglement that these one-axis twisting Hamiltonians generates. Of course, ions are not the only systems that are engineering this type of collective Hamiltonians that creates entangled states. This Hamiltonian has been implemented in cavity QED systems, in Bose-Einstein condensates, but the advantage is that the ions are going to have the controllability that are going to measure not only as I'm going to tell you, more observable, larger variety of observables that are going to tell us about the entanglement that is built up in the system. All right, so how the entanglement is built up. That's our task to understand by this very simple Hamiltonian. Okay, so let me just start by making a very brief explanation of the difference of a spin 1/2 to when you have a large spin. So when you have a spin 1/2, you have up-down, you have a two-dimensional Hilbert space. The wave function is just a superposition of up and down, and you know everything. So you can visualize the state of the system in a Bloch sphere when you look at the expectation value of X, X, Y, Z, and then you look at this vector S is telling there is two angles, theta and phi, and with that you know where your spin is pointing down. So these theta and phi are going to tell you the behavior of the wave function of the system. Now, what happens when you have a large spin? So in this case, because the interactions are all-to-all, what we are going to do is that we're going to do, instead of a spin 1/2, we're going to go to a spin S equal to n/2. If I have a spin S equal to n/2, how many states describe the system? So then there is this magnetic, the projection of SC, M, and M can go from minus n/2 to n/2. So in this case, I have n+1 possible states that span my Hilbert space. So this is the states. So I go into a space that is 2 to n+1. And still, in some degree, I am able to visualize. So the wave function, of course, is then going to be a superposition of these states from n/2 to plus n/2. Any state in this system, I'm going to be able to decompose as some of these states. And I can also visualize the state of the system now as a big spin with angle theta and phi. So then I'm going to look at the expectation value of Sx, Sy, Sc. Now Sx, Sy, Sc is the collective operator, is the sum over individual spins, and in principle I can use that to visualize the state. But this is not the full story, and I want to tell you, to emphasize that. So imagine, for example, that I have a system that is in the form of a cat state. Well, imagine that I have a system, phi, that is a superposition of minus n/2. This is the M number, plus n/2. This is a cat state, yes? So what is the expectation value of S? So this is in the C basis, yes? So M is the expectation, is eigenvalues of SC. What is the expectation value of Sx on this state? Zero, yes? It's not like a state of Sx, so you act on Sx, is going to go from n/2 to n/2 minus 1 and n/2 plus 1, so it's 0. So any eigenstate of Sc has expectation value of Sx equal to 0. So this is 0. What is the expectation of Sy? 0. what is the expectation value of SC? 0. So you see, it's a little bit more complicated because the length of the Bloch vector can go to 0. So, but still, this is not a decoherent state. It's a fully pure state, but the length of the Bloch vector can shrink. It's not necessary. This is in contrast to Pauli matrices, when this cannot happen. The Pauli matrix, when you have a spin 1/2 system, you live on an sphere because actually you always have Sx squared, xy squared, z squared are unity. But however, even though expectation value of Sx, Sy, is 0, the expectation value of Sx squared is not 0. The expectation value of Sy squared is not 0, and the expectation value of Z squared is not 0. Yes? So actually, for this state, expectation value of S squared, that is S squared plus Sy, you are not seeing that, but this plus Sy squared plus SC squared is actually always in half plus 1. Yes? So the expectation, the value, so the total S squared has values in half minus 1, even though the expectation value of S of the Bloch vector, the length of the Bloch vector, it can go to 0. So what I'm going to tell you now is that the length of the Bloch vector can be seen as a measurement of entanglement in the system. And the first manifestation that we will see that the system is becoming entangled in these Ramsey fringes is that the amplitude of the oscillations are going to shrink as a function of time. So there is not going to be oscillations because there is no rotation. I mentioned that for theta equal to 0, there is not going to be rotation, but the length of your Bloch vector is going to shrink, and the shrinking of the Bloch vector is going to tell us about the entanglement that is being built up. All right. So yes, so we are going to again repeat the sequence that I explained before. I'm going to have some theta equal to now pi half. That is the case that we are interested where mean field theory is not valid. And we are going to see in the experiment, they can measure the absolute value of Sx. They can measure, we know that there is no precession. Sy, expectation value of Sy is always going to be 0. Expectation value of Z is going to be 0 all the time because there are conserved quantities when you start with the atoms pointing along X. But the expectation value of Sx, that is what is telling me the length of the Bloch vector, can shrink. Okay, so this is what we are going to measure. So the experiment measured the length of Sx, and because this is a very simple model, SC squared, you can take yourself the task to compute analytically what is the expectation value of Sx as a function of time. And actually, when you look at this, it's a very simple function. It's a cosinusoidal function that scales as a power of n. So basically, if you try to do this, if in order to see what is the behavior of this cos n, if you have something that is cos to the n, well, it's minus 1, as a function of some variable, in this case jt, so some quantity x. And if you are going to expand with x as a small parameter, you are going to see that it's going to be 1, so you are going to have a 1, and then you are going to have something that is, so the cosine is going to be, when you expand the cosine, you are going to have something that is some powers to the n. So what happens is that it's going to be almost, n minus 1. So it's going to be something like, is similar to what we have some exponential decay. It's going to expand at short times when it's something that is going to be something like this, yes? It's going to be kind of exponential decaying function as a function of time at short times for a small x. So this is for a small x. So that's exactly the behavior that you see. So, in the experiment, you see that when they measure the contrast of the expectation value of Sx, you see that it's kind of an exponentially, like a Gaussian decay at short times. But the slope, how fast it decays, is going to depend on the number of particles. So this is what they see. So they are going to change the number of ions in the crystals from 21 particles to 100 particles. And what happens, well, there is a problem here, that is this quantity here scales with is divided by n. So when you look at here, it's going to be proportional to so it's going to square here again, but then there is a power of n here. So actually, everything is scaled like a square root of n. And that's what we saw. When we collapse all these lines as this function that goes like 1 square root of n, you see that all collapse it as we expect from the theory. So you see, well, what happens is that when this is the case when you have 100 ions and you see this behavior and then collapse as we expect. There is a little bit of decay even when we don't apply an spin-dependent force, and this is because there is light scattering in the system, there is decoherence. So that's why we need to, most of the times, currently we go to only close to the center of mass, so this decoherence is just a small perturbation on the dynamics of the system. But overall, what we see is that, yes, the magnetization collapses, the contrast collapses in a way that it scales as we expect with the number of particles. All right, so is this entanglement, what is it telling you? It's kind of boring. It's kind of, the entanglement is kind of causing the system to decohere. Can we say something else about what is the dynamics that is happening in the system? Well, and the reason is yes, and that's why in many cases we want to generate entanglement to create better sensors, to make a system enhance our sensing capabilities. And the reason is that quantum mechanically, even though, atoms are very, the energy levels of atoms are quantized in principle, and we have discrete energy states. In quantum mechanical systems, spin 1/2 systems are quite fuzzy. And the fuzziness, it means that it comes from the Heisenberg exclusion principle, that if you say you have a spin pointing along the x direction, you know that the Pauli exclusion principle, there is uncertainty in when you measure two y and z, for example. So we know very well that the system is pointing along the x direction. We have uncertainty in the other direction, perpendicular y and z. So for the case, for example, when we have a system with all the spins pointing along the x direction, we know very well the expectation value of Sx. And we know that there is no variance along x. But if we look at the variance, so Sx is in half, and there is no variance along xx, but even though there is no expectation value along the y and the z directions, we know that the variance along the y and the z direction scales like a square root of n. So this introduces noise, that is the quantum noise, it's coming from the internal quantum noise of independent particles. So the question of the point is that if we entangle the state, and in some way, we are able to redistribute this noise and make it smaller in one direction at the cost of making it larger at the other quadrature, and try to measure our quantities, our phase, in a better way. So, and that's what this Hamiltonian is doing, and it's called squeezing. If you look at the coherent state, as I mentioned before, then the variance along the x and the y direction are the same. But the point here is that when I look at my Hamiltonian, my system, and then let it evolve into this SZ Hamiltonian, then what happens is that the noise is distorted in a way that is generating what is called spin squeezing. So what is happening what is happening here is that if you, going back to kind of a mean field picture, we have a Hamiltonian that is the form chi SC squared. So at the mean field level, I can factorize my Hamiltonian like this, approximately. So what happens is that there is an effective magnetic field that depends on the expectation value of SC. Yes? So then the points in my noise that have larger SC precesses as a faster rate than points that are close to the equator and in opposite direction. And that's why, let's see if I, yes, and that's why, so if I have my sphere, initially, these points are rotating faster, these points are rotating faster, but in the opposite direction. Then this one is slower, 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 in opposite direction, and that's why it's distorting and squeezing my state. So this is good for quantum, for metrology, because it's reducing my variance along some specific quadrature, and actually, there is a quantity that is called a spin squeezing parameter, and that is actually an entanglement witness. So this is, the squeezing parameter is associated with the minimal variance. So in this case, the variance is going to be, so you try to calculate the direction at which your variance is minimum, divided by the length of your spin. And this quantity, if this quantity is smaller than 1, then you have a squeezing, and you can guarantee that your state is entangled. So it's a very useful quantity because it's an entangled witness. It tells you how useful is your state for sensing. But the drawback is that this is only a witness. So if you have something that is not entangled, it's not squeezed, doesn't mean that it's not entangled. So if you have this parameter smaller than 1, then you know that it's entangled. But if it's not, you cannot say anything about the state. All right, but we try to measure the squeezing parameter in the trap ion crystal, and indeed we see that there is a squeezing forming in the system, so they were able to measure the the quadrature where the variance is small, and the quadrature when the quadrature when the variance is small, and the quadrature where the variance is larger, so the squeezing and anti-squeezing as a function of time. This is for the case when they have a crystal of 86 ions, and you see that really the spin squeezing goes below what we expect. I mean, the system is becoming entangled. There is theory that is well reproducing what they saw in the experiment. In the theory, even we include some level of decoherence from light scattering, and very happy they were able to report 6 dB of squeezing in this state. So we were seeing the formation of entanglement, but very clearly you also see that at long times the system is losing, the squeezing is becoming 0. So the question that we had is what happens at longer times? Is the system becoming not entangled because of decoherence, or what is going on? It's agreeing with the theory, so most likely it was not decoherence, is that the system is becoming non-Gaussian, so the spin squeezing is not a good witness of the entanglement. So we wanted to understand if there is an alternative way that we can characterize the squeezing in this state. How we quantify entanglement? So let me go back, and I'm going to connect, well, let me first connect with some of the quantities that were defined in the lecture this morning, that is the idea of entanglement entropy. So, and this is what we have learned from quantum information. If I have a system described by a density matrix, and we have, well, always trace of rho is equal to 1, but if the system is pure, trace of rho squared is equal to 1. So that means that we have a closed system. The point is that if I divide my system into 2 subsystems, A and B, and I look at the reduced density matrix of my subsystem A, by tracing over what happens in the subsystem B, I construct the reduced density matrix rho A, and then what I want to see if I am going to be construct what is called the Renyi entropy, that is the trace of rho A squared, and I take the log. If the system is not a product state, well, or when the system is a pure state, if I trace over B, I'm not losing any type of information, so still I keep the system pure, and the Renyi entropy remains 0. But as soon as the system becomes entangled with the rest, and I have correlation between my subsystem A and the rest of my system, when I am tracing over the other spins, I'm losing information, and then the Renyi entropy becomes larger than 0. So this quantity, Renyi entropy, can quantify the level of entanglement that is built up in my system. So it has the drawback that, of course, is only valid for pure system, but anyway, it's giving me a quantification of the entanglement that is built up. Okay, so the question is, we can measure entanglement entropy in these systems. And well, the answer is yes, but in a very subtle way. And the way that we have to think is that imagine the simplest partition that you can make in the system. Imagine that your subsystem A is just a single spin, and we consider the B as the rest of your system. So you have A, and then you can analytically show that when you start along the x direction, that is expectation value of Sy and expectation of Sz is always 0, the Renyi entropy of a single block of your system is directly connected with the contrast, with the magnetization, the length, so Sx that we were measuring, the length of Sx. So that means if you plot the Renyi entropy, you see that it starts 0 and then grows at the maximum value that you can expect for a spin 1/2 system, because this is our qubit now, so it's going to be, it saturates at the maximum Renyi entropy that you can have for a spin 1/2 system, that is log 2, and then it saturates, and only after some time it goes back, because the system is actually, the energy levels are quantized in this simple system, so you are going to have recurrences. So, and it's exactly, this is the way that we were seeing that actually this is the way that we are seeing the contrast decay. So we are seeing that the contrast decay, in fact, is a quantifier of the entanglement that is built up in the system. And that's why we measure in the experiment, as I mentioned before. So that we are really accessing a very simple quantity in the system, that is the Renyi entropy of a single partition with one qubit, one block. But it's boring. So I mean, what we see is that it decays very quickly, and then most of the time it remains 0. So, or it remains a maximum value. So the question is if we can get more information about what is happening in the system. So maybe you are going to wonder, well, maybe you have to make the size of your block bigger. So the question is, what happens if instead of computing the Renyi entropy of one block, we compute the Renyi entropy of the half of the system? So you see that the behavior becomes much more richer. So you plot the Renyi entropy, and in the regions where the Renyi entropy of only one qubit was flat, you see a lot of structure that is going on in your system. And this happens almost, only a small, no wiggles happens when you increase the system from 40 to 60. So, and what happens actually is you are forming your quantum noise is evolving in a very funny way. And actually, for example, there is a particular time when you form a cut state. So you have your system, half of your spin pointing along. So this is exactly the state that I'm talking about along the x direction. So there is a time where your system has a cut state. Actually, in terms of Renyi entropy, the cut state is not very entangled, so you have a minimum here. But you can have also, the system is fragmenting, so you have here a cut state, you have a fragmentation of 3, 4, so it's quite rich. So at short times you see the squeezing, and then when the squeezing stops to be valid, a valid witness, you have a very nice structure of what happens in your state. So the question that we have is, can we access this type of entanglement built up in the experiment? Can we measure in some way this? And well, the answer is going to be yes, or yes, I mentioned here is a cut state. The answer is that we are going to measure yes. And actually, let me walk you a little bit, because what we are going to try to measure is scrambling of quantum information. And we are going to develop a tool to tell us a little bit of how information propagates in a many-body system. So, and this is tightly connected with the very non-intuitive idea that if I have a state that is pure, and I let the system evolve as a function of time, then what happens is that the system can thermalize. Even though the total system is pure, if I look at a subset, a subblock of my system, actually the density matrix of this subsystem can behave exactly as a thermal state. And the reason is that you can see that I can go from the case when I start with a product state, so the reduced density matrix of my system is very pure, until as a case where all the coherents die, and I actually have almost a thermal state in my system. And this is just because entanglement is built up. And this is the very nice connection between quantum thermalization in a closed system that is coming just because the system is entangled with the rest and becoming thermal, and the concept of entanglement. And this is one of the biggest synergy between, quantum information concepts are really helping us to understand the behavior of many body systems. So, and actually this idea of thermalization actually connects even with black holes, as we heard this talk, the talk this morning, where actually in black holes there was what is called the black hole paradox, that it was not understood how information was destroyed by the black hole when an object enters to the black hole and disappears inside the horizon. The question was if this information was really destroyed. And even though there was some Hawking radiation, it was not enough to compensate that the information that was destroyed. And it seems that the answer to this paradox is coming from the fact that actually information entanglement is happening within the black hole, and therefore information is not destroyed but scrambled. The system becomes highly entangled. So that's a very good connection. So yes, so the idea is that, actually the information, when the system is becoming entangled, the information is not lost, but actually is scrambling the many body degrees of freedom of the system, and the only way that we can access it back is to measure many body correlators. So only when we measure the full many body correlators, we can access and restore the information. But if I measure something that is just locally, this information is destroyed. I cannot access it. One of the pioneer experiments in colatoms that were actually to beautifully show that was an experiment done by Adam Kaufman. He is now here at Gila, where they use a quantum gas microscope. I was explaining in my first talk, this is the quantum gas microscope can really address individual atoms. So in this case, they use a change of six bosons, and they were able to measure the Renyi entropy and doing partitions from 1 to 6. And what they saw is that actually when they do the quench, that is very similar to the Ramsey protocol that we do. Well, they change the parameters of the Hamiltonian and then they later evolve, and they measure the Renyi entropy. They saw that when you have the Renyi entropy grows almost linearly with the system size, very similar to a thermal state, but then at some point it saturates. When you go to half of your system, it saturates. And after you go and measure the full system, the Renyi entropy goes back to 0 because it's a pure state. So it behaves like a thermal state initially, then the Renyi entropy saturates and then goes back to 0. So, but in these very local observables, there is the emergence of thermalization due to the formation of entanglement. And, I mean, this is a very nice and beautiful experiments in a very tiny system. You can see that the emergence of statistical mechanics just from entanglement build-up. And well, this is really nice, but the measurements were done only in a system of 6 particles. Our system can have up to 200 particles. So the question is, there is any way that we can address or we can access entanglement entropy in our system and get this beautiful information this very complex behavior that I saw in my prior picture. And well, even though there has been other experiments that are able to push the measurement from 6 to 20, for example, it's going to be very hard in our system. So we went to another approach that is not necessarily directly measuring Renyi entropy, but maybe trying to access how the information is scrambled in a many-body system. And this is another very nice concept that emerged due to the synergy between quantum information and high-energy theory. That is the idea of out-of-time order correlators. So, the speaker in the morning and very well-known quantum information theories and also in connections with high energy physics, they propose that there is a type of correlator that involves not order, the evaluation of correlations in out of time order. And this type of correlator, so here what we have is that here B and W are two operators that at time equal to 0 they commute. And this, what is called out of time order correlator, they measure the degree of non-commutativity of these two operators as the system evolves in time. So we have something, this F is 1 minus C, where C is the commutator between B at time equal to 0 and the time evolved version of W. Mm-hmm. So if the system is not commuting at longer times, it's because information is because the information is scrambled into the many body degrees of freedom of the system and make the make the state, well, it's introducing entanglement in the system. So it happens that actually very nicely, it was found that black holes are the objects that is scrambling quantum information at the fastest rate possible. So actually, there is a bound at which quantum information can become scrambled. Black holes have a growth of information scrambling that is exponentially growth, and these, they saturate the bone, where the bone of scrambling is proportional to the temperature of the black hole. Mm-hmm. And actually, they've postulated also a connection between the growth of scrambling with lambda and a type of Lyapunov exponent, and a connection between scrambling of quantum information and the formation of chaos and complexity in a many-body system. So there is these very beautiful connections that are allowed by synergy between high energy and quantum information. And the point is that if you are able to measure these OTOCS, then you might be able to see this scrambling of information in a many-body system, and that's what we wanted to measure. The question is if we were able to access these complicated out-of-time order correlations in our system. And in fact, after very soon after these correlators were postulated to be measurements of scrambling, there were different groups, including Brian Swingle, that were proposing different ways to access scrambling in a many-body system, but these proposals were a little bit too complex for us to measure. So we came up actually with a very, very simple way to measure scrambling in our system and to measure OTOCS in our system. So what we did? We used the capability to reverse the sign of the Hamiltonian in the trap ion system. So this is the protocol that we propose. So it's a type of Ramsey's spectroscopy, but with an additional time reversal step. So basically we start by preparing the system. We let it evolve with a Hamiltonian. Then we apply some rotation or some perturbation W. Now we let evolve the system with the opposite sign of the Hamiltonian, and what we then measure the quantity B. So let's try to understand why this sequence gives me an OTOCS. So, and we want to make sure that W and B commute at time equal to 0. So what is the idea? So if I'm going to follow this sequence, I start with my state 5, 0. I evolve with the Hamiltonian, apply W, undo the evolution, and I'm going to compute the expectation value of B. So this is my wave function at the time after this sequence. So this is so it's the expectation value of B, and this is the time evolved wave function. Is this clear for everyone? Yes? All right. So the trick that we use is that, okay, so this is not exactly an OTOC, but let me imagine that I use a B such that B is an eigenstate, so phi 0 is an eigenstate of B. I can engineer that. So if that's the case, I very easily can put a B here between these two, and I'm not doing anything. And then you can identify this B, the timeable version of W, a B dagger, and the timeable version of W, and I measure at OTOCS. So this is exactly the protocol that we use in the experiment. We just need to evolve half of the time with one Hamiltonian and half of the other time with the sign, the different sign of the Hamiltonian. Okay, so let me say, and I have it's very important that actually we're not at all the first ones that have measured this sequence. So actually this sequence that now we call OTOCS was measured very long time ago in NMR systems. And in NMR, they call this sequence multiple quantum spectroscopy. So in NMR, the idea, what they did, in NMR systems, they have a very highly mixed state. So NMR systems, the density matrix is almost the identity plus a small SC. You see, it's almost, if the temperature were infinite temperature, the density matrix is going to be an identity. But it's not exactly infinite temperature, but epsilon times C. That's the type of density matrix that they have in NMR. And therefore, what they did is that they choose B to be the initial state of the system. So W, they choose to be a rotation along the Z direction. So W is a perturbation that you add at the middle of the system, and they choose to be a rotation along Z. And the B is rho 0, the density matrix of the initial state. And you can see clearly that B satisfy the properties that B times phi 0 is phi 0. So it's what is the initial state is an eigenstate of B. And in NMR, they did an additional analysis of the OTOCS that is going to happen to be very useful for us. So actually, what they did is not a single OTOC, but they did so what they did is various measurements by varying phi. So this W, that is the rotation that you apply in the middle, you can measure for different angles. So you can do rotations, and what you are going to do is that we are going to do the Fourier transform. So I'm going to do my measurements, but I want to extract the Fourier transform as a function of phi. And it happens that this Fourier transform, so I measure my OTOCS, I write it in this way. Actually, this Im, that is the Fourier transform of my measure to respect to this phi angle, is called multiple quantum intensities. So this is the language that they use in NMR. And they measure like many body coherences. So actually, rho m, this is a little bit complicated, but what I just wanted to show you is that the density matrix of the system can be written in terms of density matrices that have different levels of coherence. So m is going to represent how many spin flips you have in your system. For example, an element of, if I have, this is my density matrix for a system with 3 qubits, n equal to 3. If you have m equal to 0, is the elements of the density matrix that have the same number of spins ups. So here, for example, is 0 because they have 3 ups. This is 1 because I have only 1 spin flip down. This is 2 because I have only 2 spin flip down. But I can divide my density matrix in blocks depending on how many spins are different. Yes, is this clear? So you can always decompose your density matrix in terms of matrix elements that have different coherence between them. And actually, this type of OTOC measurements actually is allow me to measure these multiple quantum intensities that is trace of rho minus m rho a. So this is, even though it's an OTOC, it's another way to see an OTOC because it's allowing to measure multiple quantum intensities. So, and this was done in NMR for many years. Okay, so, but let me show you how these measurements, so if I do many measurements of these OTOCs and I vary the angle phi, and with this I extract Im, let me see what we will see if we do that in our collective Ising model. If I do this and I plot the IMs as a function of time, this is the m goes from 0 to n. So the number of, and you can see here, and you see how it evolves in time. You see that it's a very complex object. You see that coherences start in 0, and they spread out, and they start to interfere in a very complicated way. And they clearly reflect to me, for example, why I have a chaotic state, that I have only components when n half, 0, and minus n half, for example. It's giving me the structure of the state that I wanted to. I'm not measuring Renyi entropy, but I'm measuring these multiple quantum intensities. And you can see, actually, if I plot I0, that is the trace of rho 0, and I compare this with the Renyi entropy that I showed you before, it has very similar structure. Very similar. It's not exactly the same, but the conclusion here is that even if I'm not able to measure the Renyi entropy, by measure this type of OTOCS, and in particular this type of analyzing the OTOCS in this way, I can really get information of the Renyi entropy of my system. So if I have time, I'm going to tell you a little bit how they're actually related, but it's just to show that there is really some connection between these OTOCS and the entanglement entropy of the system. The advantage here, you can see I'm not measuring individual particles. All the measurements that I do is going to be collective measurements. So this is going to be easy in experiments that doesn't have the capability of have single particle readout. All right. So how we're going to measure the OTOCS in our system? So remember that J, the coupling constant that determines the Ising interactions, is inversely proportional to the detuning. Yes, the detuning to the center of mass mode, that is the only that I want excited. So the way that I can reverse my Hamiltonian is just that I can change the detuning to the red or to the blue, and I reverse the sign of my Hamiltonian. So for us in trap ions, it's very system go from H to minus H, very simple. And the complicated part is that we measure, in order to measure the OTOCS that give me the multiple quantum intensities, I have to measure the state after the initial state, that is a fidelity measurement. I have to measure the probability, so the initial state is being down, I have to measure the probability of being all the spins down. And in principle, this is a complicated measurement, but in the ions, they cannot resolve if you have flipped one spin or two spins or three spins, but they can resolve the probability of being dark. So they can measure the probability of being all the ions in the initial state. So they can measure the fidelity that were the requirements to measure these OTOCS. So this is a way that we are accessing these multiple quantum intensities and photons. So these are actually the first experimental measurements of OTOCS in a many-body system. What we measure is this OTOC as a function of the rotation angle. And this is different times. So we see as a function of time, the system develops a little bit more structure, but it's kind of, the dots are the experiment and the solid line is the theory, but it's kind of boring. We are not seeing too much. And the reason is that after a very short time, after 1 millisecond, the signal is completely decaying. And the reason, unfortunately, is that we have a spontaneous emission. And when you measure fidelity, this is a very sensitive quantity to the spontaneous emission. And if you have n atoms, then this measurement decays exponentially. There is a decoherence that exponentially decays with the number of particles. So this was killing our signal much faster than we can see this very nice structure that we were seeing in these theoretical plots. So the experiment and the theory agree, but the point is that the signal, the I0, for example, that has this very nice structure, was decaying exponentially as a function of time, mainly because this exponentially decaying in. So we see that at time equal to 0, only I0 was 1, and the others i's are 0, and they started to build up as a function of time, but only up to I4. We needed to I of the 50 in order to see this structure, and we couldn't. So that was a little bit disappointed that, well, even though we had the tools to measure that, we were not able to see it in this measurement. So what we do in order to see a little bit more? So actually the OTOCS that we were measuring was only one specific type of observable. That this is the one that has more connections with the Renyi entropy, but still there can be other OTOCS that are not necessarily connected with the Renyi entropy that can provide information of the state. So that's what we did. Instead of measuring using B as the state of the system, you use B as the magnetization. That is something that is less sensitive to the coherence because it's not a many-body observable. This is a single particle observable. So, and instead of measuring the Fourier transform of this quantity, we measure the Fourier transform associated with this quantity. And the idea is that because it's a single particle observable, instead of decaying as e to the minus n gamma t, it decays as minus gamma t. So much more slower than the other. And what actually we figure out is that this AM is a measurement of the buildup of multiple particle correlations. What this AM tells me, if I have AM larger than 0, that means that if I compute an operator that has m different Pauli operators, so if this quantity is larger than 0, it means that there is an operator that involves m particle operators that is larger than 0. So these are building up some type of correlations, m-body correlation in the system. So it's not exactly entanglement, but it's measuring the buildup of correlations in a bigger system. So what happens is initially we have a product state, only m equal to 0 is populated, and as a function of time, I want to see A1, A2, AM, all to how many, to the number of ions in principle, that it means that the system is becoming correlated. Well, that's what we saw. So this is as a function of time. This is the experiment. This is the different AMs, and this is the theory. So you start only m equal to 0 populated, then m equal to 2 is built up, 4, 6, 8. So what we are seeing is the buildup of to a body correlation in the system, very consistent with theory. In principle, well, theory predicts that we are going to build up to 4 until the system size, but still, well, we were able to use OTOCS not only to see scrambling, but also to see actually the build-up of many body correlators. So that was nice. That was, well, it tells us that OTOCS is really helping us to access some information of the entanglement that is building up in the state. Let me say that after we did that, I mean, we are not the only group that has measured OTOCS. There has been measurement of OTOCS in an NMR system of 4 nuclear spins, and they were even able to access Renyi entropy in this system. There have been measurement of OTOCS in a Bose-Einstein condensate by kicking the system in momentum states. This was done in Illinois. OTOCS have been measuring larger chains of NMR, and they were able to probe the build-up, the many body local. So in the presence of disorder, and in the presence of disorder, actually the entanglement grows at a much lower rate. And they were using OTOCS to actually measure this slowdown of the entanglement when you have disorder. This was done at MIT in Paola Capellar group. And at JQI, they were able to actually measure OTOCS and verify that the decaying of the signal was due to actually entanglement and not by other type of decoherence. So they verify quantum, they verify quantum information in scrambling. And this is the picture, I don't know, in the morning, at the end at the end of the talk this morning, we heard that there was connection between teleportation with a wormhole. Well, this type of very simple experiment were done in a system of, say, 7 qubits when they were seeing teleportation, and they can actually retrieve the information after some scrambling of as the maximum scrambling of a unitary. So the scrambling was made by 3 qubits, and then they undo the unitary, and with some measurements, they were able to retrieve the initial information and actually testify that there was a scrambling happening in the system. All right, so there have been measurements of OTOCS, but maybe you are a little bit disappointed because we have not measured anything related with chaos, anything related with black holes. And this is perhaps our next task, is trying to understand if there is any way that we can measure access chaos and maximal scrambling in these systems. So I will not have too much time, but the question is if we can simulate fast scrambling in trap ions and make them emulate black holes. And I think the answer is yes. And the path that we are following is actually using a next level of control that is before we completely eliminate the phonons. Remember that I was mentioning, let's get rid of the phonons. Phonons are only virtually populated, and the effective Hamiltonian is just an spin-spin Hamiltonian. Well, what we are going to do, what we are doing now is not eliminating the phonons, but actually let them alive, and in addition, adding a transverse field. So involving both phonons and a transverse field. So the basic idea is that when you keep the phonons alive, and you keep them in the Hamiltonian, when you only populate the center of mass mode, is not only a simple SZ, but actually the Hamiltonian involves the detuning of the phonons with respect to the center of mass mode and of the lasers that are generating the spin-dependent force. And this term that this is the force. Remember, this is C times SC. That was the term that is spin-dependent force now for the collective system. And actually, this again, collective spins, you can see that this type of Hamiltonian is in the form of a displaced harmonic oscillator. So this is kind of C squared, and this is multiplied by C. So it's kind of a displaced harmonic oscillator. And so if you define a new bosonic operator B that is just displaced by A, by SC, you can show that this Hamiltonian can be diagonalized as B daga B times C squared. And before, what we were doing, actually in the experiment, I was cheating a little bit when I was mentioning that we were fully eliminating the ions. What we were doing actually is we were doing spectroscopic measurements at some specific points in time when the phonons and the spin were decoupled. So if you have, this is a displaced, so you can see that from this form of the Hamiltonian, this has a displaced harmonic oscillator. So a spin up are displaced along one direction, spins down are displaying along the other direction. And the point is that displaced harmonic oscillation, when they oscillate, there is a point when they decouple. So you see, if you have two displaced harmonic oscillators, they are going to oscillate each around its own minimum, and at some point, and that are multiple of the harmonic oscillator frequency, they recombine and decouple the spin and the phonons. That's where we were measuring before to remove the phonons. But now we are going to measure at any time where we measure at arbitrary time, the spin and the phonons are going to be coupled, and therefore we are going to explore not only the pure SC square interactions, but we are exploring this full Hamiltonian. So that's what we are doing. So when I decouple, is only this at this specific time, but in generally, when we have this, and we are going to add a transverse field, the Hamiltonian that we are going to create, in this case, if we add a transverse field, we cannot eliminate the phonons at all, because this decoupling points doesn't exist when I add a transverse field. So this Hamiltonian doesn't apply, and instead what I'm generating is what is called the decay model. And the decay model is a very simple model that describes the coupling between an harmonic oscillator and a spin, and a collective spin. This model was proposed by Decay like 70 years ago. And even though it was proposed a long time ago, it was not realized actually in a real system. There were some implementation in 2010 using cold atoms in a BC in the Eslinger group, but it was a mapping, so it was not implemented with real spins, but they were saying, let me assume that spin 1 is some momentum mode of the BC, spin up is one momentum mode of the BC, spin down is another momentum mode of the BC, so it was an effective Hamiltonian. The advantage is that here we can really implement directly the decay model in these trap ions, and because oh, Jesus. Okay, no. So, yes, because what is happening? Okay. So I'm going to just mention that this decay model can have a very rich physics. So even though you can write it very simple, this decay model has regions when depending of so there is a region, if you look at the energy spectrum of the decay model, there is regions when you have a statistics that is Poissonian, that the Poissonian statistics is the statistic of an integrable system, but this is a region where we have a statistics that is actually chaotic. And this chaotic system can have faster scrambling. So I don't have time to go over, but we have measured similar type. We think that by, well, this is just an idea that actually measuring OTOCS is allowing to see not only the local degrees of freedom that only have very simple information, but all the full information that we can have from a many-body system. This is from Arcimboldo, an Italian painter in the 1500s. So yes, OTOCS is allowing us to get the full information of the many-body system. So we have a proposal to measure a chaos, and we think that using the decay model, we can see exponential growth of the OTOCS. So we can, similar to black hole, we see exponential growth, not as we had before that it was polynomial growth. So this decay model does sees, not only sees chaos, but also we can see that we can see full thermalization, and we actually can access via OTOCS measurements of the Renyi entropy in these systems. So yes, so with that, so let me mention that with ions, sorry. Well, first let me acknowledge the experimental collaborators. So the experiment, all these measurements that I reported are done in the John Bollinger's group, and there is a group of postdocs here at Gila that have contributed very much to these theory calculations. And let me say that there is a great vista ahead. So we have measured OTOCS. The OTOCS that we measure is in a very simple system that is in the collective Ising model. We expect that we are going to be able to engineer the decay model, or they are working in the lab now. It's very easy for them to engineer the decay model. The only thing that they need to do to engineer the decay model is add a transfer seal and measure not only at specific times where the phonons are decoupled, but allow the experiment to measure at different times. They can implement OTOCS in the decay model because they can undo the Hamiltonian too. They can reverse the sign of the Hamiltonian completely. And we have calculations that show that the decay model does see exponential scrambling. So hopefully in the near-term future, in 6 months, we were able to see the first manifestation of fast scrambling in this system. And well, between fast scrambling and behaving like a black hole, still this is a big gap. But hopefully what we expect is that adding more complexity, so far we are only dealing with the center of mass mode. As we control the decoherence, and we can involve modes in the system, not only the center of mass, but all the different modes. Hopefully we get the complexity that is required for engineering models that actually resemble the complicated and more complicated objects, and hopefully give us some insight on how black holes behave. So yes, so hopefully in the near-term future, we can try to see quantum chaos, and we can see, beyond the semi-classical limit, hopefully we can try to see if there is something that can be useful from this fast scrambling for error correction and trying to see some, for error correction and maybe hopefully get some insight on the walls of the black hole. And well, yes, my hope was to give you a taste of what is going on in this direction in cold atom systems, and hopefully in the future, in very short term, we can have access to more interesting and more relevant systems. Thanks.